Hi, well, thank you very much for the invitation and thank you for organizing this great conference. I'm going to tell you about the formalization project that I have worked on in Lean. So I'll start by giving some motivation as to why I chose to formalize norm extensions. Then I will prove some theorems and I will tell you a tiny bit about how the proof works and some of the details of the formalization. And then hopefully I'll have time to discuss some applications to number theory. And that will be to define, formalize the definition of Fontaine's period rings. Okay. So I'll start by giving a very concrete motivation for this project. So I'll start by reminding you that the real numbers are the completion of the rationals with respect to the usual absolute value. And then if we want to look at the complex numbers, that we can get those by taking the algebraic closure of the real numbers. And well, these are algebraically closed by definition, but we also get that the field of complex numbers is complete with respect to this absolute value. Okay, but this absolute value is not the only absolute value that we have in the rationals, right? In fact, for every prime number, we have a p-adic absolute value. I won't say the precise definition, but the idea is that p is small for the p-adic absolute value. So p to the n goes to 0 when n goes to infinity. Or you can also think that if you have an integer that is very divisible by p, this integer is going to be very small for the topology induced by this absolute value. Okay, so my question is, what is the p-adic analog of the complex numbers? So first, we have to answer what is the p-adic analog of the real numbers, right? And that we already had this in Lean. This is the field of p-adic numbers. So we get this by completing the rational numbers with respect to this p-adic absolute value. Now, if we follow the previous procedure, the next natural thing to do is we take the algebraic closure of QP, QPRs, and we wonder whether this is already the analog of the complex numbers. In that case, the talk will end here, but this is not the case. In fact, some things are the same, work the same way, but some things are different, right? So we do get, again, by construction, that this is going to be algebraically closed. We get that the p-adic norm extends to this algebraic closure. And I'm going to talk a lot more about this in this talk. This is what I mean by norm extensions in this setting. However, if we look at this algebraic closure, it turns out that the space that we get is not complete with respect to this p-adic norm. So in that sense, it's not a perfect analog of the complex numbers because we do want it to be complete. So we take the completion. We do an extra step. We take the completion of QPL with respect to the p-adic norm. And now the field that we get is complete, and it is also algebraically closed. So this is what we are going to consider the p-adic analog of the complex numbers. So yeah, the concrete motivation for working on this project is we want to formalize the definition of the p-adic complex numbers. I also want to give a couple of more general motivations. So these are motivations that apply to this project, but also to some other formalizations projects that I have worked on. And these are two big goals that I would say many of the people formalizing number theory in Lean keep in mind. So the first of these goals is formalizing the proof of Fermat theorem. So this has already come up a couple of times in this conference, right? Like it's already been mentioned that this is the last theorem on Fick's list. That could be a reason to formalize it, but to me, a more important reason is that to formalize this proof, you need to formalize a lot of interesting mathematics, right? This theorem, well, it was formulated in the 1600s, but it took over 300 years to prove it. And the reason is that the proof is not elementary at all. It uses a lot of different things. You need to understand elliptic curves, modular forms, Galois representations. You need to know the modularity theorem, so you need to know class B theory. So there's a lot of things that you have to formalize here, a lot of definitions and a lot of theorems that you need to formalize. And then another, I guess, like general goal that we keep in mind has to do with the Lagrange program, which also was mentioned yesterday. Right? So the Lagrange program is a collection of conjectures that are trying to establish very deep connections between different areas of mathematics. And this is a very big research program. There are many number theories and geometers and mathematicians working in this program. And yeah, even to formalize the statement of these conjectures, like most of the conjectures are still open, right? But even if we want to formalize the statements, this will require to formalize a lot of background material so that we can get to that point. And one reason to want to formalize these statements is that maybe we learn something interesting about the conjectures in the process. Okay, so for those of you that are not very familiar with Lean or with the mathematical library of Lean, I want to give you an overview of where we are right now. So I'm listing here probably an incomplete list of projects, number theory projects that we have formalized in Lean or are formalizing in Lean. So the first few have years associated to them. So these are projects that have been published in some conference proceedings. And the ones that don't have a year associated to them are things that are still under development. Okay, so I will start by mentioning the perfect space project. So this one is not in MATLib. This was a project that was created over the library MATLib by Johan Kommelin, Kevin Bassar, and Patrick Marcel. And yeah, it is one of the goals of this project, I guess, was to bring to the attention of mathematicians that a system like Lean was able to deal with very complicated mathematical definitions. Also, even though perfect spaces are not in MATLib, a lot of the mathematics that was developed for this project is part of the library. And actually, I'm using some of it for this project that I'm going to tell you about. But yeah, what else do we have? So we have the p-adic numbers. I'm going to use that as the starting point for some of what I'm going to do today. We have bit vectors, Dedekind domains, class groups, ring of Adels of a global field. We have some stuff about elliptic curves, including from very recently that the group loop is associative, which was hard to formalize in Lean.
What was that? Can you say again?
The group loop is associative. Yeah, that was hard to formalize, but like David and Dinata and Junjan, so they formalized this very recently in Lean. Okay, so we have some basic theory of modular forms. We have group angular homology. Asni Narayanan is working on Iwasawa theory. There's a group of people working on a special case of Fermat's last theorem, so the case where the exponent is a regular prime. And then two of the projects that I am currently working on with, one with Filippo Nuccio and the other with Antoine Chamberlain, we are starting to formalize local class field theory, and we are also working on formalizing divided powers and hopefully eventually the definition of degrees. Okay, so yeah, this is just to give you an idea of what we have, and we still have a lot to do before we can dream of formalizing the proof of Fermat's last theorem, right? But we have people working on these kind of things. Okay, so now I will focus on the project that I want to tell you about today. So I first will tell you what I mean by norms. So we are going to fix a ring R. I'm going to consider a multiplicative ring norm on the ring R. This is going to be a function to the real numbers that is non-negative, such that the norm of R is equal to 0 if and only if R is equal to 0. It satisfies the triangle inequality, and it is multiplicative. So you might also want to call this an absolute value, right? This is probably the definition of absolute value that you have in mind. I'm going to need to consider also a couple of other versions of norms. So the first thing that I will say is that all of the norms that I'm going to consider today are going to be non-Archimedean norms. So that means that instead of having the usual triangle inequality, I'm going to replace this by something stronger, which is that I'm going to ask that the norm of the sum is less than or equal to the maximum of the norms of each of the elements. And then I need to also consider norms that are maybe not multiplicative. So if I change the multiplicative axiom by asking that the norm is only sub-multiplicative, that is what I'm going to be calling a ring norm. And sometimes we want to consider something intermediate. So these will be norms that have the property that they commute with taking powers, right? The norm of R to the n is equal to the nth power of the norm of R. Okay, one last definition about norms is that if we now take an R algebra A, an R algebra norm on A is going to be a ring norm on A that is compatible with the action of R. So that means that the norm of R acting on A is the same as the product of the norm of R and the norm of A. Okay, so if we go back to our original motivation, we were thinking about the field QP of p-adic numbers with the p-adic norm. The p-adic norm, it's easy to check from its definition, which I haven't shown you, that is a non-Archimedean multiplicative norm. And we want to show that we can extend this norm to the algebraic closure, QPALs, and also that this extension is unique. Okay, and more generally, if we start with any field K that has a non-Archimedean norm, and we have a field extension L over K, we can ask whether it is always possible to extend the norm on K to a norm on the bigger field L, and if we can do it, whether this extension is unique. So it turns out that both of these questions have positive answers, but we need to ask for some extra conditions on the fields and on the norm that we start with. Okay, so the main part of this project was to formalize two theorems related to extensions of norms. So one is going to be an existence theorem, and the other is going to be a uniqueness theorem. Okay, so the extension theorem, so this is the existence theorem. This tells me that if I have a field K with a non-Archimedean power multiplicative norm, and I have any algebraic extension L over K, well, the first part of the theorem is that I can always find a non-Archimedean power multiplicative norm on L that extends the norm on K. And this, this theorem also tells me what a candidate for this extension is. So it's not just telling me that there exists one norm, it's telling me that the spectral norm is such a norm. And I will show you the definition of this spectral norm in a couple of slides. Okay, so we have, for any algebraic extension, we get the existence of a power multiplicative norm that extends the original norm. And then if we also have that the extension is finite, we get a very explicit relation to this spectral norm and any other potential extension of the norm. So if I have already found some non-Archimedean power multiplicative norm on L that extended the norm of K, then I know that the spectral norm is going to be equal to the maximum of the norms of G of X, where G runs over all of the elements of the Galois group of the extension L over K. Okay, so this is the extension theorem. To get the unique extension property, we need to ask for a bit more about K. So we need to ask that, the norm now has to be multiplicative, not just power multiplicative. And we also need to ask that the field K is complete with respect to this norm. If both of these properties are satisfied, then we can always extend, the spectral norm on the extension L is going to be the unique multiplicative norm that extends the original norm, okay? So now we can go back to our example and we can directly apply this theorem, right? Because QP is complete with respect to the p-adic norm, which we have seen that is non-Archimedean and multiplicative. So by this theorem, we can extend it to the algebraic closure QPALG. And then to define Cp, we are just going to take the completion with respect to the p-adic norm. Okay. Now I'll tell you a bit about how the proof works. I won't show you all the details, but I'll give you an idea of the general strategy. So first, this is the definition of the spectral norm. Okay, so first, I define the spectral value of a polynomial. So if I have a polynomial with coefficients in K, the spectral value is going to be this value that depends on the norms of the coefficients of this polynomial. And then if I have an algebraic extension L over K, I know that every element of the bigger field is going to be the root of some monic polynomial over K. We can take the minimal polynomial, so that means between those polynomials, the one that has minimal degree. And the spectral norm of the element of L is going to be the spectral value of the corresponding minimal polynomial. Okay, so this is the norm that is going to be the unique norm extension if we have enough good properties on the original norm on K. Okay, so yeah, let me show you a sketch of the argument. The first thing that we do is we prove this lemma that if we have K a field with a power multiplicative norm, and we have a finite extension L over K, we have at least one non-Archimedean power multiplicative norm on L that extends the norm on K. Okay, so how are we going to do this? Well, we are going to start by creating a candidate for the norm. Right, so the way this works is we fix a basis for the extension L over K. We ask that the first vector of this basis is equal to 1, so that we have this condition that this is extending the norm of K. And then if we take an element of the field L, what we are going to do is we are going to express it in terms of this basis. And we are going to define the norm of the element as the maximum of the norms of the coefficients that appear in the linear combination. Okay. We could hope that this was already the norm that we wanted to use, but unfortunately we will have to do some more work here, because we can check that this satisfies the correct things with respect to addition. So this norm is already, it already has the strong triangle inequality. So if you want, this is an additive group norm. But this is not a ring norm because we don't have submultiplicativity. We have something potentially a bit weaker, right? We have that the product of x times y, the norm of the product of x times y is bounded above by some bound m that depends on the basis elements multiplied by the product of the norms. Okay, so the general strategy of the proof is we are going to perform what in the reference they call smoothing steps, which is we are going to take some norm that has some of the properties that we want, but not every property that we want, and we are going to use that to construct a better norm having more of the properties. So the first smoothing step that we are going to do is we are going to start with this norm that has this bounded condition here, and we are going to use that to construct a norm, a ring norm, so a function that is already submultiplicative and that still keeps having all of the other properties. So we never lose any of the properties. We are always going to keep adding some more. Okay, and then the norm that we get in this first smoothing step is not necessarily power multiplicative. So we have to do a second smoothing step to get something that satisfies the statement of the lemma. And I want to point out that this is really the only part of the proof where I need the original norm on K to be non-Archimedean. Because if you follow the proofs of all of the other smoothing steps, you are not really using non-Archimedean. So you are only using the non-Archimedean property to get that the norm on the extension is also non-Archimedean, but you don't use it anywhere else. But here in this step, to be able to prove even the weak triangle inequality, you need to use the fact that the original norm is non-Archimedean. But yeah, all of the other steps work in general, so I have formalized them for general norms. This is the only one where you really need non-Archimedean. Okay, so because of this lemma, we have that for finite extensions, we can always get a power multiplicative norm that extends the norm on K. Now, to finish the proof of the first of the theorems, well, first we have to prove something about infinite extensions, but that is easy because we can reduce to the finite and normal case. This is because if we want to prove any of the properties, like for example, if I want to prove, I want to prove the property about multiplication, I only need to look at 2 elements at a time. So I can always work in some finite extension. And then if this extension that I'm working with is not normal, I can take the normal closure and I get something finite and normal. Okay.
Can I just ask, so this kind of looks to be like, you know, it's an algebra lecture, but I guess you as a formalizer are like something else is going on in your mind when you're looking at these steps, and some of them say this is formalizable, and it would just be really interesting, like in that argument, what do you see as the difficulties?
Oh, I think that the part that was like the most annoying to formalize was this smoothing step where you need Nonarchimedean, because this is done with some kind of like approximation argument, like epsilon, and you have to be very careful with. Like,
there's some limiting.
Yeah.
There's an analysis involved.
Yeah.
So whenever you see analysis, you're kind of like.
I mean, so some of the other smoothing steps were easier to formalize because I was able to do that, the proofs using filters and like properties of filter scaling. But like for this one, I could not figure out how to do it without using epsilon and kind of proof. So that was the most annoying part in the formalization. But yeah, like a lot of these are defined. Well, most of them as limit or as supremums or something like that. So then you have to work with those definitions. Okay. So where were we? Okay. So we have reduced to the case where the extension is finite and normal, and then in that case we can use the lemma. The lemma tells us that we have some K algebra norm that extends the norm on K. And yeah, we do another one of these smoothing steps. For this one, I'm going to define this norm associated to the Galois group. I'm going to define this as the maximum of the norms of G applied to Y, where G, again, runs over all of the elements of the Galois group. I'm defining it this way because if you remember the statement of the extension theorem, this is exactly what I want to have. I want to have that the spectral norm is equal to this maximum. So yeah, then I use, so for this definition, I prove that this norm is power multiplicative and a power multiplicative K algebra norm on L. And then by studying the minimal polynomial and thinking about the definition of the spectral value, I can conclude that this norm is actually equal to the spectral norm. So we have finished the second part of the theorem. Okay, and then the last part is to prove the unique extension theorem. Remember that here we had some extra hypotheses. So we have the hypothesis that the norm that we start with in K is multiplicative and that K is complete with respect to this norm. So we do this in two steps. So first, we are going to check that the norm is unique. The norm extension is unique. And again, we use some argument to reduce this to checking these on finite extensions. And then, because now we are working over some finite extension and the field K is complete, then we know that the norms have to be the same. And then the last part is proving that the spectral norm is multiplicative. And this is kind of hacky. You need to do the last smoothing step. Which is you are going to fix some element Y in your field L. You want to prove that the spectral norm is multiplicative for Y. So that means that if you take any other element X times Y, the norm of that is equal to the product of the norms. But Y is fixed. You are only varying the value of X. Okay, so we used a last smoothing step to construct a power multiplicative K algebra norm on L that depends on this element Y, and this norm is multiplicative for Y. And now, because we have already proven uniqueness, we conclude that the spectral norm is multiplicative for Y. We can do this for every element, so we have that the spectral norm is multiplicative. Okay, so this is a sketch of the proof. I want to say a couple of things about the formalization. So the first one is, this has to do with how norms were defined, norms on algebraic objects were defined in MATLAB. So we already had classes, when I started this project, we already had classes like norm field, which we could use when we had a preferred norm in some field K. Right, so if I write something like this in lin, so K is a type, and then I have an instance norm field K, this is encoding a lot of information. So this is telling me that K is a field, that there is some norm on K, and that K has a metric space structure that is determined by this norm. So this is great for the base field that we are using in our proof, because we only need to consider one norm on K. However, you have seen that the argument relies on considering different norms on L, right, until we get to the norm that we want at the end. So we cannot do this using norm field instances on L, because we should only have one norm field instance, right? So to do this, what I did is I define these unbundled versions of norms on Lean. So things like ring norm, ring semi-norm, multiplicative ring norm, and so on. So now if I want to consider more than one norm on one field, so what I'm going to do instead is I'm going to take some type L, I put a field instance on L, and then I can put as many ring functions on this field and like prove anything that I want to prove about maybe how they are related or whatever I want to prove. Okay. The other thing that I want to comment is about the relation between norms and valuations. So yeah, like if you're familiar with the definition of valuation, you can think that maybe you are thinking why I didn't use these valuations instead of using norms when I started this project, because the definitions are very similar, right? So a valuation on R is going to be a map from the ring R to gamma naught. So now this gamma naught is not the real numbers anymore. This is going to be something more general. But if we look at the axioms, they are essentially the same that we had before, right? So we have the valuation of 0 is equal to 0, the valuation of 1 is equal to 1. This is, again, the strong triangle inequality, and the valuation is multiplicative. Okay. So if I want to relate these two norms, I have to restrict both sides a little bit. So in the valuation side, I have to restrict myself to valuations where this gamma naught that appears as the codomain, this is contained in the non-negative real numbers. Right, so I'm going to say that a valuation has rank 1 if it is not a trivial valuation, and there exists an injective order-preserving morphism from gamma naught to the non-negative real numbers. Okay. So with these definitions yeah, sorry.
It's a group, but it maps into
It's not a group.
a
A
monoid?
group with 0.
It's a group with 0.
Disjoint union of a group.
Yeah,
with
so it's a
zero.
group
Monoid?
union 0.
No, it's a stronger assertion than a monoid.
What's a group with 0?
It's a group.
It's a group union 0. So it's, yeah, you add a 0 element artificially, I guess.
It's a multiplicative group. So what you get from the group structure is a 1, and
Yeah.
you add a 0 on top. I mean, not on top, on bottom.
On the bottom, yeah.
And 0 absorbs the multiplication.
Yeah.
Zero absorbs, right? Zero
Yes.
is an absorbing element. It's not
Yeah.
just some random thing.
Oh,
The reals are an example, but so are the non-negative.
oh so
reals.
the
Yeah, the
unit
non-negative
element
reals,
of the
because-
group maps to 1 in the real numbers, not to 0.
Yeah,
Yes.
yeah. It's a
Okay.
multiplicative group with a 0. Non-negative reals is the key example.
Yeah. Okay, so yeah, now looking at the definitions, it's easy to check that non-trivial, non-Archimedean norms correspond to rank 1 valuations. But Lean doesn't know this, right? Like if I don't tell Lean that this is true, then I have to choose whether I want to use norm field and all of the lemmas that are proven about norm field, or whether I want to use valuation and all of the lemmas prove about valuation. So I didn't think that was a desirable situation because I wanted to be able to use both kinds of lemmas. So what I did is I created a dictionary so that if I have a norm field structure on a field K, and the norm is non-Archimedean, then I can create a valued structure, so a valued field structure on K. And conversely, if I start with some field L, in which I have a rank 1 valuation, then I can create a norm field structure on the field. Okay. So now, if you do this, so I could have done this for Cp, I guess, but I wanted to do this in general, right? I want to be able to do this for every field in which I have either the norm side or the valuation side. So yeah, now we have access to all of the lemmas, I guess. Okay. And yeah, any questions so far? Yeah.
Yes, and then once you have the translation, how do you deal with the statements that deal with one definition or one or the other?
Yeah, so once I have the translation, I can have both instances on K, right? So I can have a norm field instance and a value field instance, and these are compatible, so they are not going to cause me trouble with it. So I can use both lemmas coming from each of the theories. Yeah, I had to prove something for this to work. Right? I had to prove that the uniform space structure that you get in both cases is the same, so that you don't get, you don't confuse Lin, I guess. But once that is done, you can use lemmas for from norm fields or from value fields.
And do all of these things have some bundled uniform space in somewhere?
Mm-hmm. Yeah.
Is this dictionary in Mathlib already?
Not yet, but yeah. Yeah, I mean, this is pretty independent from the rest of the project, so I could PR this one. Okay. Yeah, so I think I have some time to speak about the last part of the talk, which is formalizing the definitions of Fontaine's period rings. But again, I want to give some motivation as why formalize these rings, right? And for this, I want to start by talking about Galois representations. So I'm going to fix a p-adic field K. For example, K could be the p-adic numbers. And I'm going to let GK denote the absolute Galois group of K, so Gal KL over K. P-adic Galois representation is going to be a continuous group homomorphism from this GK to the general linear group of V, where V is some finite dimensional QP vector space. So one example of interesting Galois representation is the étale cohomology of a proper smooth variety defined over the field K. Yeah, we also, when we start with a Galois representation, we often wonder whether this representation comes from geometry, right? So here, for example, I have a number field F, some fixed prime number P, and I am given some finite dimensional p-adic representation of the Galois group of F. Well, Fontaine and Mazur have a conjecture that predicts whether this Galois representation is going to come from geometry, in the sense that it's going to be related to some étale cohomology of some variety. I'm not going to get into the details of what these conditions are. I just want to point out that one of the things that you have to check is that at some finite collection of primes, you have to check that the restriction of this representation is the run. I'm not going to say what that means, but this is a property that Galois representations can have. Okay, and
in statement 1, should the second P be the other kind of P?
No. Oh.
Mm-hmm.
Otherwise, the quantified variable is never used.
Yeah, I guess.
Oh, yeah, sorry. Yeah, that should be, the other thing. Thanks. Okay, so, yeah, the insight of Fontaine was that he realized that he could use certain rings to detect properties of Galois representation, like being the RAM, but also some other properties that are interesting. So he defined Fontaine period rings. These are rings satisfying a certain collection of properties, so they have to be a topological QP algebra V with some continuous linear action of the Galois group, often with some compatible dictional structures, so for example, something like a Frobenius map. We ask that the points of V that are fixed by the Galois group form a field, and we also ask that this, we can create this this vector space, and we ask that this vector space is some interesting invariant of the Galois representation. And we are going to say that a Galois representation is B admissible if the dimension of this vector space that we have defined is equal to the dimension of the QP vector space V. Okay, so why do this? Well, because for different choices for this ring V, we can detect different interesting properties of the Galois representation. So I'm going to show you here the first few examples. So the first one is take the algebraic closure of K. Then the property of being admissible for the algebraic closure is equivalent to the Galois axiom factoring through a finite quotient. If we, instead of K alpha, we take V is equal to the p-adic complex numbers, we get that V is Cp admissible if the action of the inertia group factors through a finite quotient. Then the last one that I formalize is V-hot state. So V-hot state is the Laurent polynomials on Cp. And being V-hot state admissible means that the representation admits the composition of this form. Okay, and then the last one, I haven't formalized it yet. I'm working on the formalization, but it's not finished yet. And this is the one that appears in the previous conjecture, right? So, so B has this property of being the RAM if it's admissible for this ring V the RAM. And the definition of this V the RAM is kind of complicated. Like you have to define a bunch of rings. So this is a sketch of the definition. So first, we start by defining E as the inverse limit of OCP mod P. And then A inf is going to be the bit vectors of E. Remember that we said that we already had bit vectors in Lin that I was going to use them. Here is where I'm going to use them. Okay. And then B inf plus is going to be this ring A inf adjoin 1 over P. So we localize away from P. Okay. We need some more steps. The next step is the one that is missing. So, we need to formalize. We need to formalize that there is a canonical surjective homomorphism from this ring B plus to the complex p-adic numbers. And then, once we have this map, we can define V the RAM plus as the completion of B plus with respect to the kernel of this map. And finally, V the RAM is the ring of fractions of V the RAM plus, but it turns out that this is actually a field. Okay. So this is what I wanted to present today. Thank you very much for listening, and please, if you have any questions for me.